let us continue with the discussion what we had in the last lecture. This lecture we will discuss more about response spectrum in a stochastic process. We already said that the mean value of the force realization is 0. This implies also that the mean value of the response process is also 0. Hence, force realization set f of t, if it is a stationary process, one can assume f dash as follows. F dash of t can be f of t minus m f. In that case, this will also have mean value as 0. X dash of t can be said as integral 0 to infinity the transfer function f dash of t minus s ds, following the same algorithm what we discussed in the last lectures. This will amount to the integral of the transfer function minus integral of the transfer function ds, because f dash is actually a process containing this and this, which now I can say as this of course will give me x of t and this of course will give me mx. So, now I can say x dash of t is given by this equation. I will continue with the same numbering what we had in the last lecture. For x dash of t to have a 0 mean value, f of t and f dash of t should have same auto-covariance. That is a statistical requirement to establish this fact. Having said this, then xj of t and xj of t plus tau, a small interval, can be expressed as 0 to infinity h fx s1 fj t minus s1 ds1 multiplied by the other integral, which is hfx s2 fj t plus tau minus s2 of ds2, which now can be written as double integral h f x s1 h f x s2 f of j t minus s1 f of j t plus tau minus s2 of ds1 ds2. I call this equation number 16. We also know that expected value of x of t and x of t plus tau can be expressed as limit n tends to infinity 1 by n of summation of j equals 1 to n xj of t xj of t plus tau. Hence, the double integral which we shown in the last slide, which is s fx s1 h fx s2 can be expressed as limit n tends to infinity 1 by n of summation of j equals 1 to n fj t minus s1 and fj t plus tau minus s2 ds1 ds2, which can be further simplified as double integral f x s1 h fx s2 expected value of f of t minus s1 f of t plus tau minus s2 ds1 ds2, which can be said as double integral h fx s1 h fx s2, the autocovariance function of tau plus s1 minus s2 ds1 ds2. Now, since f of t is assumed to be a stationary process, expected value of x of t plus tau will be independent of time. Therefore, the autocovariance function C x of tau which will be as same as the autocorrelation function R x of tau, since the process is also a zero mean process. The autocovariance function or the autocorrelation function can be given by the double integral of the transfer function of Cf of tau plus S1 minus S2 ds1 ds2. I call this equation number 17. Having said this, let us move towards the response spectrum. Let us say S of x omega be the variance spectrum of the response process x of t and S f omega be the variance spectrum of load f of t. then the variance spectrum of x of t is defined by the Fourier transform of the autocorrelation function, which is given by x omega is 1 by 2 pi minus to plus infinity the autocorrelation function minus e I tau omega d tau, equation 18. From the earlier equation, equation 17 gives an expression for Cx of tau. Let us substitute this in equation 18. So, in that case x omega will become 0 to infinity h f x s1, 0 to infinity h f x s2, 1 by 2 pi minus to plus infinity the correlation function of tau plus s1 minus s2 e minus I omega tau d tau ds2 ds1. So, in the above equation, let us substitute tau plus s1 minus s2 as theta. Then d theta is d tau, hence Sx omega will be given by 0 to infinity the transfer function 0 to infinity the transfer function with respect to S2 1 by 2 pi minus to plus infinity the correlation function in terms of theta e minus I omega theta d theta e I omega S1 minus S2 ds2 ds1. So, this equation can be further simplified as 0 to infinity h f x s1 e I omega s1 ds1, 0 to infinity h f x s2 e minus I omega s2 ds2 and s of omega, which can be now written as h f x minus omega h f x plus omega s f omega, which is s x omega is given by this equation. This is true because E of minus I x star is as same as E I x, and we all agree that the transfer function h of x t is a real function. Therefore, capital H f x of minus omega will be 0 to infinity the transfer function e I omega t dt, which can be said as 0 to infinity h f x t e minus I omega t star dt, which can also be said as 0 to infinity h f x of t e I omega t dt of x star, which can be said simply as h f x omega star. Having said this,